Dear students, I welcome you all to this tele-learning session. I must say that I am not going to bore you with complex mathematical analysis or terrifying equations. Rather, I must say that for the next few minutes, I will discuss or we will discuss on some beautiful ideas in physics that has shaped our contemporary world. Now, before starting our journey, let us discuss or let us say, start our journey with a chant from the famous Brihadaranyaka Upanishad, Tamosoma Jyotirgamaya, Tamosoma Jyotirgamaya. That means lead me from the darkness to the light, lead me from the darkness to the light. And when we are talking about light, light is a fascinating things that has encouraged, that has affects our day-to-day life since a time immemorial, that people have believed that light is God and light is with God. Then light is also the origin of and evolution of all types of living organism, starting it from the basic primitive form to the complex living organisms, may it be the humankind itself. Now, let us say when we start our journey towards the wonders of light, a a number of charming images will come into our mind clip after clip. Let us witness some of those clips screen after screen. Now, you may say the glow of a lighted candle, twinkling of stars, a beautiful sunrise, the sunset, the rainbow, the colorful soap bubbles, and the sunlight coming through the trees, sunlight reflecting in atmosphere, then sunlight coming through the doors, the reflection of street light on the wet roads, and many more such things has fascinated all sorts of people of all ages throughout years to come. But at the same time, a quite difficult question, a quite alarming question comes to everyone's mind, that light, whether it is a particle or a wave, light that we see, does it have particle-like property or wave-like property? In the 19th century, physicists were quite puzzled because light that we thought to be a wave, in some experiments it started behaving like as if it were a particle. Now, the question is, why it is like that? Take an example of one experiment, photoelectric effect. In a photoelectric effect, what happens that you take a metal plate, here, and when you shine light at this metal plate, when you will shine light at this metal plate, what you will observe? You will observe that this light will knock out electrons in the metal. This light will knock out electrons in the metal. So, this is the electron here and this is the light, and we have seen that when it strikes this metal plate, it strikes the electron out of the metal, provided the light has got a sufficient energy to do that thing. When we try to explain the phenomena behind this, the theory behind this, the contemporary wave mechanics failed to explain the same, or by using this wave mechanics we get the wrong result. Then it was sorted out by taking a clue from Planck's description of a light, that a light can deposit or deliver energy in terms of small packets, in terms of discrete packets. So, using this analogy, Einstein was able to explain the theory of photoelectric effect, was able to describe how this photoelectric effect worked, and also able to predict the experimental outcomes that was measured actually in the lab. So, he even gone to the extent that these light waves, when incident upon the metal plate in discrete or metal plate, we can thought it as incidence of discrete packets of energy consisting of some energy h nu, where h is Planck's constant, where h is your Planck's constant, and this nu is your frequency of light. Is the frequency of light. Now, taking this into account, when a photon or when a particle of light or when a light is incident upon the metal surface, these packets of energy delivers the entire energy to the electron or none of it. By considering this idea, it has put all the pupils into a dilemma that initially light, what we have thought as a particle, now behaving or thought as a wave, now behaving as a particle, because at that time it was already established that light was a wave. From the famous, let us take the example of the famous double slit experiment performed to study the diffraction of light. What we have observed, take a double slit here, this is the screen here, and this is say the source of light. If light was a particle or if light was a bunch of a particle, then when a light is shown at this double slit, we will find that the light particles will pass either through this hole or through this hole. So, what we will get? We get either a bright spot here or we will get a bright spot here. That means, assuming light to be a bunch of particles, we would have get two bright spots on the screen. But instead, what we have observed? We have observed a distinct diffraction pattern on the screen. We have observed a distinct diffraction pattern on the screen because of the light emanating from the two slits overlap upon each other or superpose upon each other. This diffraction pattern, this experiment clearly suggests that light was a wave. But on the contrary, the photoelectric effect has established that light is a wave, light is a particle, and this double slit experiment has established that light is a wave. Now, this shows that light can have particle-like properties as well as wave-like properties depending upon the experiment that has been conducted. So, we can say one thing that finally the physicists are settled to this point that a light at some time behave as a particle and at some time it behave as a wave depending upon the experiment that we conduct. This preliminary idea gives us an insight to the concept of a photon or concept of a light particle. And with this we can say that when a matter, with this we can say that when a matter interacts or with a light, or we can say when a light interacts with matter, it behaves as if it contains packets of energy. It contains packets of energy, and these energy packets are known as quantum. These energy packets are known as quantum. Now, each energy packet or each quantum has some definite energy h nu and momentum h by lambda. The fact that they possesses a definite energy and a definite momentum allows us to attach a particle nature to light, and this particle of light is known as photon. Is known as your photon. So, what we can say that photon is the consequence of the interaction between light or radiation with that of your matter. So, we can say light, since light is a wave or light has got a dual nature, we can have the wave nature of light explaining certain phenomena like interference, diffraction, refraction and polarization, whereas photoelectric effect will be able to explain the phenomenon like your photoelectric effect, Compton effect and all other phenomena to come. Now, with this we will study some of the basic features of photon. Now, what we can say that a photon is nothing but an energy packet that gets deposited due to interaction between light and matter. We can say that these photons, have an energy E equal to h nu or h c by lambda, where nu is the frequency of light, lambda wavelength of light. We can say that these photons move with speed of light c equal to 3 into 10 to the power 8 meter per second in vacuum. These particles are electrically neutral, which exhibits that they are not deflected by electric and magnetic fields. So, we can say when a photon interacts with an electron, the electron or the collision is perfectly elastic in nature, that is, the total energy and the total momentum remains conserved. But during the collision, the number of photons may not be conserved, that is, the photon may be absorbed as observed in the case of photoelectric effect, or the photon may be redirected or a new photon may be created as observed in case of Compton effect. So, what we have learned so far, that a photon or when a light has got dual nature, that sometimes it behaves as a particle and sometimes as a wave depending on the experiment that we conduct. Secondly, that due to interaction between a light and particle or light and matter, it behaves as a discrete energy packets called a photon travelling with the speed of light, and you can say that the imparted energy equal to h nu and momentum h by lambda. Let us now discuss some of the significant facts about photon. Photon has a rest mass 0. How in this world can a photon have a momentum when they don't have any mass? Does it necessarily mean it will make the wavelength infinity? Let us now discuss to the first fact that photon has got a rest mass 0. What do we mean by that? That photon has got a rest mass 0 and how it possesses a momentum. Now, from relativistic mechanics, m equal to m0 divided by square root of 1 minus v square by c square. That implies m0 equal to m whole into square root of 1 minus v square by c square. Now, for a photon, v equal to c. So, 1 minus v square by c square equal to 0. That implies your m0 equal to 0. That is, a photon has got a rest mass 0. Now, come to the second part. How it has got a momentum? From a classical analogy, we have P equal to mv. When m equal to 0, then P will be equal to 0. But this is true only when particle moves with a speed less than speed of light or not comparable to speed of light. So, when a particle or things move with the speed of light, then what happens? We have got the relation E square equal to P square C square plus M0 square C fourth. Now, when M0 equal to 0, we can have E square equal to P square C square implies E equal to PC, that implies H nu equal to PC, that implies your H by P equal to C by nu equal to lambda. That implies P equal to H by lambda. So, we have observed that even though a photon has got a rest mass 0, yet it has got certain momentum P equal to H by lambda. And from this expression, if we write lambda equal to H by P, we will find that this will give the wavelength of light, and here P is your momentum. Here P is your momentum. So, what we have observed, since a photon cannot be at rest, we can say that the wavelength will not tend to infinity. Rather, we can say that your wavelength has got some finite value. Now, come to the next point. What if? Now, come to the second question, that what if light, we know that light and light particle can only deposit some discrete amount of energy and not any less than that. Now, question is, how much energy each photon will deposit, and why did physicists never discover this before? So, on coming on to this question, we can say, we know that light departs energy in terms of small packets, and these packets are called photons. And energy of one photon equal to h nu, where h is your Planck's constant. And its value is 6.626 into 10 to the power minus 34 joule into second. So, what happens here, since h is very small, this value of energy is also very small. To be specific, I can say that if we consider a violet photon, its frequency is 7.5 into 10 to the power 14 Hz. And the energy of one violet photon is something about 5 into 10 to the power minus 19 joule. And this energy is very, very small. And if you will say how much small is this energy, I am giving you an analogy. The analogy is that in a professional baseball league, a baseball player throws a ball with an average speed of 100 joule. Can you tell that how many such violet photons will emit or will deposit this much amount of energy? The answer is that this is equivalent to energy deposited by 2 into 10 to the power 18 number of violet photons. So, this energy is so small that it is hard to notice that such a small energy can be detected. So, this is the reason why physicist has never noticed this before. Now, come to this third question, come to the third point, that why is it that the visible light only emanate or exhibit dual nature? To explain this thing, I can say this much, that energy is directly proportional to nu, and your wavelength is directly proportional to your small p. Since p directly proportional to square root of E implies lambda directly proportional to 1 by square root of E. So, this shows that the light having greater frequency will have greater energy and hence smaller wavelength. So, these lights will exhibit more particle behavior than wave behavior. This is why your gamma photons, X-rays, etc., they exhibit more particle behavior than wave behavior. Similarly, in case of low frequency photons, the energy is low, so it behaves more like a wave than like a particle. So, only visible light, since it comes in the medium frequency range, it has the suitable energy, suitable frequency to exhibit both particle as well as wave nature. So, what we have learned so far, that a light exhibits dual nature, it can behave as a particle or as a wave depending on the experiment that we conduct. Light delivers energy in packets having an energy h nu, where nu is the frequency of light. These packets of energy are called photons. Each photon has an energy h nu and a momentum h by lambda travelling with speed of light. So, we can say that through his revolutionary idea, Max Planck has paved the way for many revolutionary findings in the world of physics, and truly he was said the messiah of, or the father of modern quantum mechanics. and for his contribution to the world of physics, he has been truly awarded the Nobel Prize in 1913. And this has for the concept of photon and a description of your electromagnetic or blackbody radiation in terms of photon. In early 20th century, when the particle nature of light was discovered, that light deposit energy in discrete energy packets or photons. We call this particle of light as photons, and we have assigned the characteristic features of photon. Then when every other scientist, everyone else was worried about light, whether light behave as a particle or as a wave depending on the experiment that they conduct, in 1924, a French physicist Louis Victor de Broglie was proposed or came out with an astounding idea. He predicted something that was not explained by anyone, and the idea was completely new. He told that when a light or photon is incident upon the metal, an electron is ejected. This light has got or exhibit particle nature, but he asked that what about this electron? What about this electron? We know that light sometimes act as a wave and sometimes act as a particle. He said, if light which is thought to be a wave act as a particle, maybe this electron that we know as a particle can act as a wave, or we can say that the electron may have certain wavelength. Now, what we are speaking? We are speaking of a particle having a wavelength. This has confused many contemporary scientists, because till that time it was established that a light or electron is a particle. Now, with these ideas, what he tries, he actually tries to synthesize the idea of a matter and radiation, rather the light particle and the particle actually into one framework. What he does? He even predicted the wavelength for this electron. He predicted wavelength for this electron as a lambda e. He depicted it as de Broglie wavelength. He depicted it as de Broglie wavelength. He even gone to the extent of hypothesized the value of this wavelength as lambda e equal to h by Pe, where Pe stands for momentum of the electron. Now, the question is, from where he has get this result? He got this result by correlating the fact or correlating the idea with the wavelength of a photon that we have studied earlier as lambda photon equal to h by p. And by correlating these two ideas, he has come up with the idea that an electron has got a wavelength lambda equal to h by Pe. Now, come to the interesting fact. if you are saying or if you are assigning wave nature to an electron, then how is it that we are talking about a matter having a wavelength, and even in this universe, even in this world, how we are going to test this thing? And for this thing, again the Young's or again the double slit experiment for diffraction of light come into the rescue. Now, what he has done or what it has been proposed, that in a case of a double slit experiment, if light is allowed to pass through this double slit, we have observed a pattern like this. Now, if light is a wave and when it passes through this double slit gives a wave like pattern, and if we are saying that electrons behave as a wave and possesses certain wavelength, then while passing through this double slit, it must exhibit the diffraction pattern or wave like pattern. With this idea, in 1927, two scientists, Davison and Gormer, reperformed this double slit experiment using electron. And what they observe, that if this slit width are of atomic dimension or atomic dimension of spacing between crystal planes, then what he observed, if this was a particle, we would have got two bright spots, but since it exhibit wave-like behavior, we get the diffraction pattern as observed in the case of light. So, this proves that de Broglie was right, that every matter particle is associated with certain wavelength and they behave as a wave depending upon the experiment that we conduct, and for this analogy he has been awarded with a Nobel Prize in 1929. Now, let us come into the fact that how de Broglie was able to speculate his hypothesis, and to speculate his hypothesis he has come into or he has considered two assumptions. The first assumption, that the two physical quantities that govern the entire universe are mass and energy, and from Einstein's mass energy relation E equal to mc square, so that there is a complete equivalence between matter and radiation. And secondly, since nature loves symmetry, we can say that since light or radiation have a dual nature, therefore matters must also possess dual nature. Due to that reason, we can predict that electrons, protons, neutrons and other fundamental particles as they move exhibit wave-like properties. Now, let us discuss how de Broglie was able to explain this hypothesis and was able to derive the wavelength for the particle. Now, let us say that, let us say that a light of wavelength lambda is incident upon or is moving in space, say. Assuming this to be a wave, assuming it as a wave, E equal to hc by lambda, and assuming is as a particle, E equal to mc square. As wave and particle has got equivalence, we can write hc by lambda equal to mc square. That implies h by lambda equal to mc, and that implies lambda equal to h by mc equal to h by momentum of photon. And for any other particles, we can write lambda equal to h by mv, where v is the velocity of the particle. Now, let us discuss the consequences of this de Broglie wavelength associated with material particles. Now, to consider that thing, let us say, write down the expression for de Broglie wavelength, that is lambda equal to your h by p or equal to h by mv. Now, if p is large, then as lambda directly proportional to 1 by p, lambda will be small. That is, the particles having greater momentum will have small amount of energy. Now, let us relate this into some other thing. We have lambda also directly proportional to 1 by square root of E. That means that greater the energy of a photon or greater the energy of a particle, smaller will be its wavelength. So, greater the energy, it is difficult for us to visualize the wave nature. Let us give an example. Suppose, consider this is a red photon and this is a violet photon. If we will observe the wave pattern, you will observe this is the wavelength here, and in the case of this violet, you will get this is the wavelength here. You can see the difference. It has a low energy, it has high energy, and see the difference that you get in either case. Let us now come to another consequence. Bit 2, lambda equal to h by mv. What if the particle is at rest? Then v equal to 0 and lambda tends to infinity. What does this infinite wavelength signify? That means the wave nature is not defined because something by 0 is not defined. So, here the particle will not exhibit any wave nature. Now, come to the third point. The de Broglie wavelength is independent of charge and nature of the particle. That is, may it be an electron or a proton, it will have same de Broglie wavelength if they have got same energy or same momentum. And fourth point is, de Broglie wave cannot be electromagnetic in nature. That is, only accelerating charge particle exhibit your electromagnetic waves. Now, come to the fifth point. Why the macroscopic objects in our daily life do not show wave-like properties, such that a truck is moving, a car is moving, you are moving, why you are not exhibiting wave-like properties? Now, to come to that point, let us discuss the formula here. We have lambda equal to h by mv. Now, that implies lambda directly proportional to 1 by small m. If m is large, lambda is small. This is why in case of macroscopic object like bus, truck, human beings, animals moving, we are not able to visualize the wave nature. Now, with this idea, de Broglie has tried to determine the de Broglie or particle or de Broglie wavelength of an electron. That means the wavelength associated with a moving electron. What it does, he has considered that an electron being subjected to a potential difference of capital V. So, the kinetic energy of the electron will be equal to half m v square, and which is nothing but equal to small e into capital V. Since K E equal to P E square by 2m, that implies P E equal to square root of 2m K E or square root of 2m E V. This determines the wavelength of electron as lambda E equal to h by P E equal to h by square root of 2m K E, and which is equal to square root of, or sorry, this is h by square root of 2m E V. So, this is the expression for de Broglie wavelength of an electron. If we will put the value of h, mass of electron, and your charge of electron, this comes out to be lambda E equal to 12.3 or sorry 12.3 divided by square root of V, this much angstrom. Now, where V is your potential difference the electron has been subjected to. Now, what is the significance of this result? Now, let us consider that the electron is subjected to a potential difference of 100 volt. Then the wavelength associated with it will be 12.3 divided by square root of 100, and it will comes out to be 1.23 angstrom or 0.123 nanometer. And this distance or this wavelength is of the order of the spacing between atomic planes in a crystal. And this is the reason why in 1927 Davison and Gomer was successful in observing the diffraction pattern of electron by taking the slit width of the order of atomic planes in a crystal. So, this astounding result leads to a question that taking this lambda equal to h by Pe, taking this relation lambda equal to h by Pe, and the idea from de Broglie that why Bohr's atomic model was a successful one. That means taking lambda E equal to h by Pe and the idea from de Broglie, you can show why Bohr's atomic model actually worked. I am not going to solve this. This is a question that you will think. I am just giving you a hint. The hint is that what is the most significant point or postulate of Bohr's atomic model? That it was able to eliminate the drawbacks of your Rutherford's atomic model, that electron revolving in a particular orbit is rather stable. That means electrons revolving in a particular orbit does not radiate any energy. How is it that electron is a charged particle, and when it moves under the influence of a nucleus, another charged particle, according to quantum theory, it should have continuously emanate light. Then how is it that the electron revolving in a specific orbit, in a particular orbit, does not radiate any energy? And why these orbits are called energy levels lie in this fact that lambda E equal to h by Pe, and lies in the fact the way de Broglie has explained these ideas. For this outstanding idea, de Broglie was awarded a Nobel Prize in the year 1929 after his postulate being subjected to experimental verification in 1927. This astounding work of de Broglie has paved the way for many scientists to show the advancement in quantum mechanics. So, and the journey begins here. Surely, after de Broglie's paper, Edwin Schrödinger came across and basically set the stage for the rest of the quantum mechanics. So, in this discussion so far, we have tried to make a journey through the golden era of physics in general and quantum mechanics in particular. This particular era has witnessed many revolutionary ideas, starting from Planck's concept of light deposits energy in terms of discrete packets, to Einstein's explanation for photoelectric effect considering light to be consist of photons. Then de Broglie came forward that when a light behaves as both as a particle and a wave, so also every material particle in this universe behaves as a wave depending on the experiment that we conduct. This leads to a golden era of quantum physics, which is the stepping stone of modern physics. I hope you have enjoyed this work with me. Thank you.